Hey everyone, and welcome to today's Explainer. If you've ever stared down some advanced statistical theory and felt like you were trying to navigate a dense, maybe somewhat intimidating landscape, you are in the perfect place. Today, we're taking a highly complex mathematical abstract and translating all those heavy formulas into a fascinating logical journey. We're looking at a truly foundational paper in probability and high-dimensional statistics. And I promise, by the time we finish, you'll see the elegant, surprisingly intuitive story hidden right inside the math. Okay, let's dive into this. To make sure we don't get lost in the weeds, we have a very clear roadmap today to break this down into digestible steps. We're going to hit 4 main sections. First, introducing the covariance ensembles. Second, breaking down the matrix. Third, linking sample to population. And finally, building better estimators. Starting right off with Section 1, introducing the covariance ensembles. So, the source material for our explainer today is a prominent paper titled Eigenvectors of some large sample covariance matrix ensembles. It was put together by Olivier Ledoit and Sandrine Péché and submitted to the ArXiv database back in November of 2009, nestled right under the probability and statistics theory categories. This paper tackles a notorious problem you hit when dealing with massive datasets. And honestly, their approach is absolutely brilliant. Moving right along to Section 2, breaking down the matrix. And here it is, the main sample covariance matrix formula. Now, I know the notation looks pretty heavy at first glance, right? But the architecture here is actually incredibly elegant. We're going to act as your translators today and break this machine down piece by piece so you can see exactly how it operates. Now, what's really interesting about this is how each specific piece has a very manageable job. X sub n is simply a real or complex matrix of size n by p with independent and identically distributed entries. Then we hit this specific condition, a finite 12th moment. I know, finite 12th moment sounds like a dramatic sci-fi movie title, but it's literally just a mathematical boundary condition for our matrix entries to keep the numbers from spiraling out of control. And finally, we have sigma sub n, which is defined as a positive definite matrix. Just to make sure we've got the foundational building blocks locked in, let's quickly define that last parameter. In this context, our positive definite matrix, sigma sub n, represents a strictly structured, symmetric n by n matrix. Its primary job in this equation is to scale our sampled data properly. You can kind of think of it as the underlying structural foundation that just forces the rest of the math to behave the way it should. Which brings us to Section 3, linking sample to population. To do this, we've got to look at what are called asymptotic conditions. Basically, we're asking what happens as our data parameters stretch all the way out toward infinity. Condition 1 assumes that as n approaches infinity, the spectral measure of our scaling metrics, sigma sub n, almost surely converges to a limiting probability distribution. Condition 2 dictates that the ratio of p to n approaches a positive constant, denoted by gamma. So, in plain English, we're dealing with truly massive datasets where both the number of observations and the number of variables are growing super large simultaneously. And, this perfectly illustrates the core challenge of the entire paper. We have a strict dichotomy here. On one side, we have sample eigenvectors. This is the stuff we can actually observe and calculate from our finite real-world data. On the other side, we have population eigenvectors, which is the underlying unobservable mathematical truth. The problem is, when you have tons and tons of variables, the sample eigenvectors distort. They drift away from the true population eigenvectors. Quantifying the exact relationship between these two is the beating heart of this research. So, to bridge this gap, the authors introduced this rather complex functional formula to study the asymptotics. And yeah, it is a heavy piece of notation. But mathematically speaking, it's absolutely crucial. It's the exact bridge connecting our flawed observable sample data straight over to the true population reality. Let's swiftly define these variables so we don't get bogged down and lose our momentum. I is just the identity matrix. Think of it like the number 1, but for matrices. G is simply a bounded function, basically keeping our mathematical outputs within a sensible range. And Z is a complex number. By feeding these specific components into the functional, the authors can track exactly how those sample eigenvectors behave as the dimensions scale all the way up toward infinity. All right, the final stretch, Section 4, building better estimators. So we've waded through the theoretical weeds, but you might be wondering, why? Why go through all this complex math? Why calculate these wild asymptotic limits just to compare sample and population eigenvectors? What's the actual end goal here? Well, here is the payoff, and it's straight from the final sentence of the author's abstract. By successfully quantifying this relationship, they are, quote, paving the way for a new generation of improved estimators of the covariance matrix and its inverse, end quote. Because they finally figured out exactly how the sample eigenvalues distort under massive scaling, this math literally allows us to compute an asymptotically optimal bias correction for sample eigenvalues. Basically, they figured out how to mathematically reverse engineer the statistical distortion and clean up the data. How cool is that?
Let's quickly summarize the journey we just took, because it shows exactly how theoretical math turns into a highly practical statistical tool. Step 1, they identified that crucial gap between observable sample eigenvectors and true population eigenvectors. Step 2, they applied those complex asymptotic functionals to quantify exactly what that bias looks like. Step 3, armed with that deep knowledge, they computed an asymptotically optimal bias correction. And finally, step 4, they empowered the whole statistical community to develop a brand new generation of improved estimators.
It's just an incredibly elegant solution to a massive problem in high-dimensional statistics. And, it leaves us with a pretty fascinating thought to close on. If mathematically correcting sample bias is actually possible, even as our data dimensions stretch toward infinity, what other statistical boundaries can we push next? Thank you so much for joining me on this explainer. I really hope this structured breakdown helped illuminate the brilliant architecture hiding behind the math. Keep learning, stay curious, and I'll see you next time.